Hello everyone and welcome to the Autodesk Robot Structural Analysis tutorial brought to you by the Civil Engineering Essentials channel. I hope you enjoy the video. In this video we are going to take a look on the different aspects of modeling simplified rafts or mat foundations in Autodesk Robot. Now this is a video I've been waiting for a long time because it enables me to revisit some videos where I was simplifying my earth or ground connection as a simple support, be it fixed or roller. But after we finish this mat foundation video, maybe in the future we will visit some of those videos and apply raft foundations and discuss the difference between the results when there is a raft foundation versus the results when there is no raft foundation. So to start with, I'm going to select my 3D building design. Of course, an important note here is that I'm going to rely heavily on the Principles of Foundation Engineering, a book by Braja M. Das. It's a 7th edition. And it talks about mat foundations in the chapter 6. And of course, before I start, I need to give you a small theoretical background about this. When designing mat foundations, there are usually two methods to design those mat foundations. There is the conventional rigid method, in which case the mat is assumed to be perfectly rigid, infinitely rigid, and that the soil pressure distribution is a plane. Now this is the rigid method, but of course it has all the kinds of shortcomings because you are assuming a rigid mat foundation, whereas your mat foundation is not rigid. So an improvement here is the approximate flexible method. In the flexible method, as you will see, the mat is supported by soil, which is modeled as an infinite number of elastic springs. And well, let me show you a very quick example for that, because remember, this is a simplified video. So let's say that we have a raft foundation that supports the following columns. So I have columns at, I don't know, like 0 at x, 4 in x, and 9 in x. And let's say we have also, I don't know, like 13 in x. Also in the y, I have 0, 5, 9, and 12. Or let's keep it like that without a 12. If you apply now, here you have the column centers, but there is something missing. You see, when you model a raft foundation, usually the raft foundation extends beyond the column. The reason behind why a raft foundation extends beyond the column is because you are going to make sure that the raft or mat foundation doesn't fail due to punching shear or beam shear or the liking. So it's counterintuitive to actually put the raft exactly, or to put the column exactly on the edge of the raft. So what actually makes sense is to have x at -1 and also x at 14, so 1 meter before, 1 meter after. Of course, you can make it larger if you want, but I just keep it as 1 meter. Of course, you can change it if need be, for example, if the punching shear fails. And in the Y, I'm also gonna extend the raft 1 meter in each side. So if you click apply now, you can see that the outlines of the raft foundation are now visible. How can I model a raft foundation? Well, it's a floor, but this floor now, before you draw anything, you need to define the thickness. And here is where the fun starts. So you see, the first question you need to ask is how thick the raft foundation is going to be. Now, the thickness here is a trial and error system, meaning you would assume a certain thickness, apply the loads, design your raft foundation, check if the design works correctly, and if need be, you can increase the thickness, or for economical reasons, you can decrease the thickness and keep trying until you reach the most economical thickness. Of course, we are not designing here, we are modeling, so we will not be doing this iterative procedure. Maybe when I have a full building, I will do that, because soon enough, we will be starting modeling full structures. One important question to ask is, how can I have an initial assumption for the raft foundation that makes sense? And for that, I'm going to share my own experience. Of course, this is an experience based on the region I'm working in, and feel free to share me your own experiences. So an experience I have personally is we use, for high-rise building up to 10 stories, we use 100 millimeters per each story, meaning with a minimum of 350 millimeters. Meaning, if you have a 7-story building, I usually start my raft assumption at 700 millimeters. If I have a 9-story building, I usually start my assumption of the raft at 900 millimeters, and so on. Of course, if I have one-story building, then I'll then basically assume that the raft foundation for a two or one-story building is 300 millimeters because that's the minimum, or 350 sometimes because that's the minimum I personally am accepting. Okay, so I'll just say here, like I'll call this thickness, I don't know, uh, 600, so I'm assuming it's a six-story building, and then R for raft, so I have 600 millimeter here. Remember, it's your responsibility to design the raft. I'll talk about the design of rafts of a raft foundation later, but today I'm only on the modeling aspect. So you are responsible for checking this thickness and making sure that it's good to resist all the forces applied on the raft. Now, if you simply just click on add, this means that you just added a thickness 600 for a roof, but this is a raft, and the difference between a raft and a roof is that you have parameters of foundation elasticity. And this is where the book Braja Imdaz comes into play. So if you click on foundation of elastic if you click on parameters of foundation elasticity, you're greeted with the following simplistic window where you can input the spring coefficient in the z-axis and the spring coefficient in the x and y axis, and you can use the Braja MDAS reference to calculate a spring coefficient that is adequate. Now, to continue this video, it's very important to understand what the parameter of foundation elasticity should be. Now, there are numerous references that link the soil with its corresponding soil stiffness or the spring stiffness. So, of course, those values are outtakes from Raja Imdas's book. So, if you have a foundation which has a width of B and a force Q, then of course the stiffness here is Q over delta, where delta is the settlement that the foundation will undergo, which basically corresponds to the stiffness of the soil. Now, how do you find that? There is an equation in Braja MDAS which gives you K equals K 0.3, which is here a stiffness found out from testing a foundation, a standard foundation that is 0.3 meters by 0.3 meters wide. It's a square plate measurement that is done, field load test if you want, and you can relate your spring constant from that test. Of course, there is in the same reference, Braja, it talks about different assumption values for the subgrade reaction based on the soil type. This is a very generalized thing, but I want to talk about this a little bit. So, okay, I have this reference in my hand, and let's go and try this out. So I will basically let robot do it himself. So if you click on basically calculation of K coefficient of elastic foundation coefficient, you can see that robot allows you to add soil layers as you see fit. So I'm going to ask for sand, similar to the Braja MDAS reference. So I just basically try, see if what the difference is between what robot does and what the reference does. So I'm trying to find the sand that is similar. So I don't know, I'm trying now. So once again, we want 50 meters by 10. So you have 50 meters in the A and 10 in the B. It's once again flexible because I closed that. And I think now we are ready just to say OK and see what the calculation is. The calculation is 23,715 kilonewtons per meter cube. So I'll just basically write this on the paper here. Okay, so if I click OK now, it will implement, or if it doesn't implement even, you can just copy that if you want, and just close here and implement it here if you want. Now, this is what robot calculated, but what about our reference, Raja MDAS? So if you go to the equations that I've explained just now, let's say we have some sort of medium sand. Now you can see that the ranges are all over the place. That is totally okay because inherently geotechnical engineering is a little bit dangerous, and things vary it a lot. Of course, there are, I mean, Braja MDAS is a reference, but there are, of course, other references that, for example, connect the soil elastic spring modulus, or K. They connect K not with Q, not with delta, not with the type of soil, but they connect the K spring coefficient with the bearing capacity of the soil. It depends on the code you're using and on the design practice you're using. For me, I have a reference and I will stick to that. So, okay, let's say that I'm going to take the average here. So this is basically 75. So my K03 is 75 meganewtons per meter square. And I'll apply this here, where B is your width. So if I take my calculator and calculate this very quickly off screen, and the answer I got on my calculator is 19.78 mega newtons per meter square. So I got from Braja Mdas's reference 19.78 meganewtons, which corresponds to 19,780 kilonewtons meter cube. And for robot, it was, I think, 23,715 kilonewtons per meter cube. It's not really that close, but it's nothing to blame here because it just chose arbitrarily the average value here, and that's the reason why it was lower, to be honest. Now, of course, you see that Braja Mdas's recommendations here are quite wide margined, meaning that, well, you will have those variations, but at least it's good to see that things are somehow a little bit on the same order of magnitude. Okay, so with that being said, I will stick to robot's elastic foundation coefficient. I will assume that there is no uplift. I'll add that. So now I have my Raft foundation ready to be defined. So I click on add, close, and now I have it here, 600R. And I can basically click a rectangle and select all those points just to fill up my Raft foundation. And I have now a Raft foundation. Now, one thing that you could make a mistake in is not to check that you are at story 1 4 meters. So if you go to view, you will notice that your raft is now flying in the air, which is counterintuitive. So it's good to click it, basically go to edit, move, and move it 4 meters down. Please notice that this actually, even if it's flying on top, will not affect the calculation results. So I have my foundation right now. Now I'm going to quickly add me the forces. So the first case, I will add me some nodes like this. So I'll just basically start clicking here. Oh, I misclicked, I think. I need to delete this. So let me just delete that very quickly. And I'll continue clicking and adding nodes as for the basically columns that will carry the loads to the foundation. So I'll just basically click them very quickly. And now I'll just calculate I have a dead load case and a live load case. And I will assume that there are some areas here. Let's say that this column is responsible for this tributary area. And I have to off-screen calculate this very quickly. I need to find a quick estimation for the load. So give me a second. I'll do this off-screen. Or I just thought maybe you want to see this very quickly on screen. So I'll click on the structural axis and take a look. So I have 3 types of columns, maybe 4. I have the corner columns, and I have the middle columns, and I have those corner columns. I will assume that all corner columns are the same just to speed up the calculation. So if you look here, you can actually, if you forgot, you can actually go to tools and ask it to open the dimension lines and basically start dimensioning your stuff so that you can remember what kind of dimensions you had. So you can see this is 4 meters. I'm assuming that the raft is extending beyond the columns, but the roof that the columns do support does not extend. Because if it extends, then I have to calculate the balconies I take them into account when calculating the loads. Okay, so how do I calculate the load? I'll assume that there is a live load of 4 kilonewtons per meter square and a dead load of 10 kilonewtons per meter square. Now I need to know how many meter squares each column carries. This is called the tributary area method. Of course, it's less accurate than the reaction method. The reaction method is what you use when you model your full structure. So for this 9-meter column, the tributary area is going to be 2 meters here. It has a tributary area of 4 meters, which means that its live load for 1 story is 4 meters square multiplied by 4 kilonewton per meter square, which is 16. This is for 1 story. So I write the number 16 here. And for dead load, it's 4 by 10, which is 40 kilonewtons for 1 story. Now I have 6 stories, 6 slabs. So this means that the load here, and I told you I'm going to unify the load on all the edge nodes. So I click on other load. We are in the dead load now. So it's 40 kilonewtons per slab, which means 40 by 6 is negative 240. And this is applied to all those nodes. So I basically start clicking and selecting those nodes, and you can see that I have applied my 200, I think 40, I think it was 240 force on those nodes. Okay, fantastic. Now going on, the tributary area is 4 and 2.5 is 4.5 multiplied by 2. 4.5 multiplied by 2 is 9 meters square. I'm doing a very quick in-head calculation. I'm not using a calculator, to be honest. So pardon me if there is a small mathematical mistake. Anyway, the area here is 9 meters square. This is for each story. The dead load per one story is 9 multiplied by 10, which is 90. And the live load per story is 9 multiplied by 4, which is 36. This is for one story, which means that for all the stories, it's going to be 90 by 6, which is negative 540 kilonewtons. And I'll just add that to the dead load case, and I'll add this to all the nodes that are on the edge like that. So I'll just click those two guys, and I know those might be different, but I will just include them anyway to save some time. So I'll just add that, apply this, and you can see that the loads here are now applied. They are 540 kilonewtons. Going on for the internal columns, I have 6 multiplied by 200, which is 1200 kilonewtons. I'll add that and add those loads to my internal column, which are just 2. So apply that. Now I have all my loads in the dead load. Okay, now in the live load, I have a nice trick up my sleeve. Instead of recalculating this entire thing, I can go to loads, load table, and show you a slight trick, sleight of hand, to show you how you can convert the dead load to live load. This is only here because there is a ratio that is between the live and dead loads. You can only do this trick right now, and this is very important to notice. I want to reiterate this again. You can only do this trick now because you are not having any own weights, so the only relationship between the dead load and live load is the surface load. So I basically copy paste. I just copied and pasted, Control C and Control V those cases. Now first of all, I'm going to switch them to live load, as you can see. And to make sure that they are switched, if you go to view, you can see in the dead load that those loads exist, and you can now see also in the live load that those loads exist. So let's see. Those are in the live load, and those are in the dead load. It's the same forces. Now we're not finished. We need to modify this. So when you go back to your load table, you see the dead load was 10 and the live load was 4, which means that the live load is 40% of the dead load. Since there is no own weight for the elements, the only thing that affects the load is basically this ratio. So this column, which has 240 in the dead, is going to have the 0.4 of this value, which is going to be, I don't know, like 100. So I just put 100 here. I think it's 96, but let's keep it as 100 just to make sure. This one will have 0.4 of this value. I just said 200 for the sake of simplification. And 1200 multiplied by 0.4, 480. And now I'm done. If you close this and see, you see that you have your live loads defined. Of course, you can go to loads manual combination and apply a combination 1.2 dead plus 1.6 live. And yet another combination that you have to do is a combination using the service loads. Depending on the design code you're using, usually the bearing capacity of soil is measured from the service loads. So it stands to reason to create a combination from loads manual combination. But this time you click on new, and you can make it SLS. I'll keep it ULS, but I'll just make sure that it's 1 dead load plus 1 live load, and this case is going to be used to check the soil pressure beneath the foundation. Alright, fantastic. So I click close, and now I'm ready to start analysis. Of course, I will be faced with a lot of problems right now, but let's, for the sake of just having fun, calculate or start the analysis. So you start the analysis, you will have some isolated nodes and of course some instability, and you can see that there are some instabilities of type 2 at node 89. Now, why is that? It's that because when I defined the foundation elasticity, you can see that there are some springs here. The reason being is, now why are there some springs here? The reason behind the springs is because I enabled them. If you go to display, you can enable in the model the elastic foundation. So if you remove that, there are no springs now. But if you add that, basically if you click on this elastic foundation, you get your springs back. and those springs are what hold the elastic foundation in place. Now, if you click on deflection shape, you can see that it deflects quite normally. The internal columns have more deflection than the external columns because they are under more force. So what I'm trying to say is that this instability can be ignored because our forces are in Z and our reactions are in Z. But still, let's entertain the thought. You see the instability here is in direction UX and UI and so on. So let's try see what's the matter with that. Now, first of all, the instability in UX and UI is not dangerous because there is nothing pushing in the direction of UX and nothing pushing in the direction of UI. So to address the instability, you can go to thicknesses here, which is you defined there. Double click on this to modify the definition. And you can add some stiffnesses in the X and Y axis. I'm going to add me 1, although I doubt that 1 is going to be enough to stop this. So even if it doesn't stop, I will not be addressing this too much right now. I will be addressing this maybe later when you have full structures, because there is nothing pushing in the X and Y. Well, it seems that this placeholder 1 that I have added in KX and the placeholder 1 that I have added in KY was good enough to hold the structure in place, and now there are no instabilities. So that's the first thing I wanted to talk about. The second thing I want to talk about is the deflection shape. We want to take a look on the settlement. So if you click on maps and click on UZ like this and click on apply, you can see that the deflection is quite high. I mean, you look here, you see it's 4 millimeter, and it could shock you. But wait, of course, if it could shock you, then you need to increase the size of your raft. But before you decide or not decide, let's discuss some issues here. First of all, who decides if a settlement is more than the allowed limit? Of course, the code and the engineer decides that, and this decision making is something I will leave for you. So before you rush to your code, I have a small piece of information I want to share with you. You see, if you go to maps and open the description, you can see the values are spread on those raft. Now, you can see that the deflection, or the settlement in this case, is 3.91. Now, you need to remember something from structures. It's not only the settlement that is extremely dangerous, but also the differential settlement. And the differential settlement is the settlement between two supports of a beam. Now, this structure, of course, has a superstructure that I didn't model, and it is going to have beams in the horizontal direction like this and beams in the vertical direction like this. So I'm interested in the difference between this point and this point, because the beam is going to run on the other stories. It's going to run on that direction. And you can see that the differential settlement here is 0.5 millimeter. Now, I don't know about your code, but I think a differential settlement of 0.5 millimeter is okay-ish. Here you have a differential settlement of 0.9, which, I don't know, it depends on your perspective. I think this is still in the green light. Now, why didn't I compare this point with this point, 2.23? The reason being is because there is no beam that connects between the maximum load here and this. This beam will connect those 3 points. So 2.63 and 3.1 have a 0.5 millimeter differential settlement. And the same goes for those two guys, which has almost 9.9 millimeter differential settlement. Of course, I'm checking my deflections using the service loads. I'm not combining them, so it's 1 dead load plus 1 live load. So okay, this is about the differential settlement. Now, to continue, how do we design this? The design of this is going to be the talk of a different video, because I want to mention some practical aspects in designing raft foundations, especially because I'm planning to have a different video that talks about rafts when there are some positions where it's thicker than the other positions. Here you have a raft of constant thickness. You can even see this if you click on display and click on model. You can actually, or click on panel, you can actually open the thicknesses and see it for yourself. You can see that this is a constant thickness. Now, sometimes you have rafts where it's not constant thickness, and I will talk about this and the design of rafts in a different video. Now, just to mention, if you go to results, maps, and click on MXX, you will see the moment of the strip in X. If you go to MYY, you can see the moment in the strip of MYY. And of course, you can see all kinds of stuff like the shear force and so on. Now, you can improve the visualization of this map by going to results, and I've explained this before in a video called panels. You can go to panel cut, and you can use the panel cut to basically visualize this contour map as a two-dimensional drawing. So I click on panel cut, make it parallel to my XZ plane, click here, hit the apply button, and make sure that I see what I want to see. We have in the map the value for mxx, so in the cut I want the value mxx. Fantastic. I click apply and close, and you can now see the contour visualized by the means of a panel cut. And this is how you would design. Those are the moments that you will use to design your raft. Now, one last important thing I want to talk about is the soil pressure, because in the end the soil has a bearing capacity. And if you click on Soil Reactions K and click on OK, you can see the soil pressure in kilonewtons per meter square, of course, or kilopascals. Now, of course, here you need to double check those values with the values provided by the soil laboratory, and it depends on your soil type. If those pressures exceed what the laboratory suggests for your soil, then you should consider increasing the size of your raft. I will leave this decision for you because I don't want to mix a lot of things in one video. Maybe I will talk later in a full example where I have an architectural drawing and I have my soil lab results, and I actually simulate for you how I would design a structure from architectural drawings and from all those inputs like the soil lab report and so on. But for now, I will just leave it as is because I want to consider one thing at a time. The second thing I want to talk about is a small personal thing I usually do. You see, here you have really high moments because, of course, we are in the service load. You should go to the ultimate load. But still, the same logic applies. You have extremely high moments. The reason behind having high moments is because you have a concentrated load applied on that point. Now, in reality, columns are not applying concentrated loads, but are actually distributing the load on a small region below their cross section. So this should be modeled as an aerial load. The second thing I want to talk about is to tell you that also the raft itself within its own thickness distributes the stress on the soil. This is for the people who are worried about the soil reaction. This is a little bit inaccurate, and there is no way a finite element software can do it accurately. But I just small hint to you. Yeah, fantastic. Now I see the thickness. Now what I'm trying to say is the load that is applied on the raft gets distributed using the 2-to-1 method or whatever your method you see fit, meaning that this load actually arrives at the soil not as a point load but as a distributed load on an area. So that's the second thing that I want to talk about when comparing what you get in the finite element method of what versus what you get in real life. The last two things I want to talk about in this video are, first of all, a small thought experiment by changing the load here to a distributed load. And the second experiment I want to do is I want to show you a different way of modeling a raft foundation. I don't recommend that, but I just want to show you that this exists. So I'll just take that. And first of all, I will remove all the calculations and remove the mesh. So I click on the mesh tool, click on X and remove the mesh. Also, I will just remove the force labels because I want to see things. Now I'll take this and copy it twice because I want to do some comparisons now. So I'll just basically click, copy or move. I'll copy it twice and I'll move it, I don't know, a distance 20 in the X. I hope this is enough. Is it? Let's put it 30. No, 25. Yeah. While I'm doing this, I want to mention when do we use mat foundations. Now, I was taught in the university that, of course, you have spread footings and you have combined footings and you have mat foundations. And it was like a small idea that if your footings cover 70% of the ground, then you should switch to a mat foundation. I'm interested in hearing your own thoughts on this. At least this is what our experience has taught us. Anyway, so I will talk about this in a moment. I will delete this load first and also delete the live load. I mean, just make sure I'm not messing something up. So the dead load is now no longer here and the live load will be deleted. So let's delete it on the live load. So let's click on delete. Okay, and now let's apply us a different type of load. So I'll go to dead load now and I go to my loads and let's discuss this a little bit. I want to add a surface load. Now I want to apply me a area load. Now I run the analysis very quickly for reasons I'll explain in a moment because I want to eyeball it very quickly. I don't want to really talk about this in detail. I'll assume that the size of my column is this big. Now I know this might be inaccurate, but just want to show you what happens if you take the size of the column into account. So this time I want to have not a distributed uniform planar load. I want to have a uniform planar load on a contour. So I click on that right now, and I want this time to have a planar load. Now it's a long story, and I have to make sure I know what I'm doing. So I just click on Tools, Dimension Lines, and make sure I understand what I'm doing. So I need to know the area, because I'm gonna calculate distributed load. This is 2 meters. This is also 2 meters. Okay, so the area of my column is 4 meters. Now this is a ridiculously big column, but that's not the point. I want just to show you something, an idea I have in my mind, to show you the effect taking the column size into account. Of course your column is smaller than this, of course. I just want to show you what happens with the soil pressure if you use the columns. Now, since my column is 4 meters big, the load here is going to be distributed as an area load. So 1,200 divided by 4 is going to be 300 kilonewton per meter square. So I'm going to put here a 300 kilopascals, because kilonewton meter square is a kilopascal. And this time I will define my contour. So I'll click on contour definition, and I want to define my contour like this. 1, yeah, that's right. 2, 3, 4, 5. And now I'll apply it here. Isn't it? Okay, I'm trying to apply that. Hopefully it will work. Apply. Yes. Fantastic. I have my first load. So this is my first load, that is the dead load. Now, instead of going through this entire torture again, I'm going to go to my load table with my nifty trick. I'll copy this and paste it. And I will remember, wait, it didn't paste. Okay, paste it, please. And remember that the relationship between live and dead is going to be 0.4. So 300 multiplied by 0.4 is 30 by 4, which is 120. This is for the live load. Of course, I need to switch my case to live load. Close that and take a look on my live load. You can see 480, 120, and so on. So I'll run the analysis now. Now, please notice this is a ridiculously big column, but I just want to show you what happens when you take the column size into account. Of course, the column is smaller than this, so whatever you see here is actually less than the real thing, but I want to show you only, the point here is to show you the effect of having the column spread out. And you can see that when you start taking the column size into account, this spike in moment no longer exists. Of course, my column here is extremely huge. It should be smaller than that, and but the point I'm making still stands. You know what? I think I should. I'm better than this, so I think I should improve this. So I think this is a little bit annoying. I will improve it here this time. So this time I will make it even better here to show you what happens if I try to mimic a column. Here I just made a ridiculously big column. Here I'm going to make me a smaller column. And now I want to define me a better column. So this time I want to define my column as in reality. So I think this was, okay, this is 29 meters. I'm adding some grid lines here. So I want 29 meters. Let's say that my column is 700 millimeters by 700 millimeters. So my x is at 29, which means that I will have 29.35, so 350 millimeters, and 28.65. Also, my y, I'll click here again, 5.35 and 4.65. Add this, apply, and close, and now I should have my 4 points here. This is my column now, and this time my column is actually not ridiculously big like this. No, this time we're going to enjoy having a real column, because, we should make sense of this stuff. Fine, this is big, I'll just keep it for the sake of just showing you this. So for now, I will do the same thing, but this time I remember that the area, and I have my calculator right beside me, it's 0.7 multiplied by 0.7, which is 0.49 meters square. Now the dead load is 1,200, which means if you take 1,200 divided by 0.49, the pressure here is going to be a whopping 2,450 kilopascals. So I'll go to loads, go to surface loads, click here, and say this is negative 2,450. Wow, that's a huge load. Oh, I don't need this. And then I select contour, and this time it's whopping 2,450 negative. And I'll select my contour this time, being 1, 2, 3, 4, 5. That's my contour. And I apply this to this plate. Seems doesn't apply, so I click here, select that, and hit the apply, and I have it here. Now this is for the dead load. Of course, I need something for the live load, so I'll just go to loads, load table. Once again, use my nifty trick. This is only possible because I don't have own weights in the structure, so the relationship between dead and live is 10 to 4, meaning that I can easily select here live load, sorry, and multiply this by 0.4. So 2450 multiplied by 0.4 equals 980. So I have 980 here. Hit the enter key, close, and now I'm ready to analyze. And this time this makes more sense. I run the analysis right now, and I want to compare two key values. So now I have taken the size of the column into account, and the reason why I'm doing this is because I want to show you the difference between using point loads and using the actual size of the column. So if you go to the moment now and click OK, you can see the difference between this value here in dark blue and this value in less dark blue. Of course, this is extremely small because my column is really big. It's ridiculously big, but you can see the difference. Now, let's put this into numbers. Now, for the case, for example, for the case of live load, for example, just to get a sense of numbers. If you click on results, maps, and let's say we want to see some values, so I'll just basically click on values and click here just to see what the value of the moment is. Now remember, I don't care about the case. The only thing I want to see right now is the relationship between the moment under a point load and the moment under an area load. So if I click here, this is I think 180, so I write this on my piece of paper right now, which is getting progressively full. I go here, take a look, it's 85. So if you calculate this, 85 divided by 118 multiplied by 100%, what you get is, you get that the moment under a column that takes the column size into account is 72% as large as the moment under the column that uses a point load, because a point load is like a needle, whereas a distributed load is the correct way. So this is more accurate, to be honest. And you can see that this is 81, 83 something, so it's like 70%. There is a reduction of 28% here. This leads to the second advice I have to you, my dear engineers. What I am doing when I design structures is, you see this moment underneath the point load, I totally ignore, and I have a reason why I ignore it. I'm not ignoring it because I just want to ignore it. No, because in reality this is what happens. So what I do when I design is, I don't take the moment underneath the point load directly, because this is an overestimated moment, but I move a little bit away, and not a little bit away, I move exactly 0.35 away, and you can see that the moment seems to start getting correct values. Take a look. I mean, let me show you. So let's take a moment here. I'll click here. This is like, I don't know, this is like 87, all right? So if you go to here, the edge of the column here, which is this one now. This is too much. I told this is overestimated. But if you go to the edge of the column, you can see you are at 93, 92. So what I practically do, is that I don't take the moment underneath the point load to design. No, I go a distance which is the width or half the width away of the column center, because this is a little bit more accurate, whereas this is an overestimation. The reason being, I have just showed to you this logically and without a shadow of a doubt. The reason is that your columns are not basically a needle that applies pressure on a raft. No, your column is basically an area that applies a stress on your raft. Finally, if you go to going back to the soil reaction, you can see the difference in soil reaction. The soil reaction here is 21.05, whereas the soil pressure underneath this is 21.95. Not really a big difference, but well, it was more a difference in the moment diagram thing. So of course, you can click on maps to see the colors. You can still see that the danger zone is really large here, whereas here the danger zone is mildly diluted. Anyway, I hope this is a quick idea to see the difference between using columns as needles and using columns as area load as they are supposed to be. So here I want to spice things up, so I want to show you a different method of defining a raft. Now, first things first, I need to remove the foundation elasticity from this raft, so I have to basically define me a new thickness thickness 600 without the parameters. So now this is a perfect slab. It's not supported. And if I apply right now this to this and run the analysis now, I should have an unstable structure because this one is going to fall down. See, it's unstable. And if you let him continue, I will get a deflection that is, I don't know, like 1 million or something. You see, the deflection here is 1 million, meaning that this thing is falling down. Of course, doesn't make sense because it's not supported. Anyway, to support this now, I will support it using not a elastic foundation, but I will personally define my support. I'll go to nodal now, and I will define, instead of planar, I will define me a nodal elastic foundation. And this time I will basically define a spring for UZ. Now the spring here is kilonewton per meter, but what is the value of the spring? Now this is extremely technical, but the idea here is that I think this was 2 meters. Let me just quickly check. Yeah, it's 1 meter. Okay, fine, fantastic. So the foundation here is 1 meter. I'll just delete that very quickly. So this is responsible for a 1 meter by 1 meter area. Now, if you remember, the foundation elasticity that robot used was 23,715. Now, luckily for you, the tributary area for the node is 1 meter, so I can use the same value, luckily for us, for all the nodes except the nodes on the edges, because the nodes on the edges are going to be different. So I'll just add this and go on top and select all. I just here say, wait, I need to rename this. So I'll say here S internal. And now I want to apply one else. And this time I will choose, because on the edge they only have half the area, so they will have half the stiffness. So with my calculator, 23715 divided by 2 equals, and this is going to be 11857.5. And before I add this, I will call this support edge. And I'll add that. And now I will add my corner support, which is going to be yet again half of this, because my corner is only a quarter of the real area. So this is going to be 5928.75. And it's a spring in the Z. Now, of course, this might not work. I'm going to try that, to be honest. I'm in the dark here. And I'm going to call this support corner. And I'll add that. Now, let's do it. So, first of all, I want to add my support internal, just to double check. Okay. And I'll click this, like this, and click the apply button. And now I have reactions here, which are going to be springs. Now, on the edges, I will basically select those guys here, and those guys with control hit it, and those guys, and those guys. And I hit the apply button. Finally, for the corners, I'll just click support corner and select this corner, this corner, this corner, and this corner. And I click the apply button. So yeah, I think I have now made a mattress made out of springs. So I don't know, let's try. Maybe it works, maybe not. I don't know. So let's try and run it, hoping it works. And the only thing I can know if it works or not is to check the deflection between the Raft and the springs. So let's take a look on the deflection shape. And yeah, I think, oh, okay. Oh, nice. I think I'm happy now. Let me just, oh, really? I think it worked. Okay, let's take a look. So I'm not really sure if it works or not. I'm still skeptic. Now, of course, I will not take a look on this one because here I have added my improved loads. I have to compare apples with apples, so I'll compare this with this. And I think, technically speaking, they seem to be the same. I'm getting happier as I'm talking, but I need to make sure, of course. So I go to maps, results, maps, and I'll select the deflection in the Z direction, just make sure. And let's take a look. So I'll just go there and select value and just stand here. It's 0.92. And I'll go there. I don't think it's going to be 0.92, right? Really? Are you? Oh, hey, you are. It works. Wow. It's the same. Okay. Okay. I'm genuinely happy now. All right. Now, does the moment work too? I mean, really? Okay, look at that. It's almost identical. It's almost identical. Now, there are some differences here, but it's almost identical. Oh, I'm proud of myself, to be honest. Now, this is amazing. So, to understand, okay, now what just happened? Just recap. I just defined me some springs. Of course, the spring stiffness was the earth stiffness multiplied by the tributary area of the spring, which means that I had to define me 3 springs, one for the internal nodes, one for the edge nodes, and one for the corner nodes, and it worked out fine. Now, there is, I think, this will not work, right? It will not work. Yeah, of course it doesn't. Yes, okay. Now, okay, good, good. So let's talk about this. Yeah, sorry, I need to collect my thoughts because I'm a little bit ecstatic now. All right, so to collect our thoughts, I was able to mimic the foundation by basically putting tons of springs below the foundation. And this actually gives me an idea to implement in my software Strado, but I'll keep this in my head myself. So I mimicked the foundation by putting tons of springs, and you can see that, okay, this works just fine. Now, there is one disadvantage for using springs instead of foundation elasticity. That is, you cannot see the reaction of soil, because you can see here the reaction of soil happens because you defined a soil stiffness, a soil elastic foundation. But here you didn't define any soil, so the robot doesn't know that. But is there a trick to know it? Not really sure, but I have an idea. If you go to results, diagrams for members, I think, and you go to reactions, let's apply. Now, I should be able to see the reactions, right? Let me just check. I want to see them all, so okay. Okay, I'm seeing the reactions. Okay, I think I have a good idea about this. So if I open description, I'm really typing in the dark here. 21, what's this? 21? Is it 21.86? Is it? Really? I don't think so. Wait. Wait a minute. So what is this? Where are you, man? You are 21.86. You are below this, which has the maximum load, right? Right? Show me. It has. God, look at this. It's 21.86 as a reaction, which is exactly the same as the soil pressure. Now, this is what we're talking about. Now, I think there was a diagram, right? Does it work for... It doesn't work, no, right? It doesn't work. Of course it doesn't, because this diagram works for linear supports. We have planar support, so it doesn't work. But, I mean, yeah, still. Okay, just to make sure, this is 3, right? So is this 3 there? I don't think so, no, right? Is it? Let's take a look. Okay, it says 11 here, but I don't know. I'm still happy that I got at least 21.86. This is really magnifico, as they say. And, okay, this is, but wait, maybe I messed up. This is below the force here, right? What about the other force? Other force. Yeah, it's still 21.86. Okay, fine. So, yeah, we done that. I'm sorry, this video had a lot of internal monologuing, and I don't think I will video edit this. So I'll just keep it like that, my inner mumblings, because I want you to see inside my head what I'm thinking of. Anyway, I hope that you enjoyed the video, and please note, I apologize once again for the video about the cylindrical walls and domes. I'm not really happy of it. I think this is like not rising up to the standard I'm trying to put in this channel. So this video is basically a redemption video. The video that I've explained today opens the floodgates on all kinds of videos I can do, because now I think I made peace with rafts, so I can use them in future. Anyway, I hope that this video was beneficial for you and that you've enjoyed it. If you have enjoyed the video, please like, share, comment, subscribe, especially subscribe, because it helps increase the reach of my channel. This is the Civil Engineering Essentials channel, and we will catch you in the next video.